Making the transition from ship to shore is one of the biggest challenges the military face. Carrying troops and tons of equipment across the ocean and into some of the planet's most hostile environments presents a seemingly impossible problem.
We have to move vehicles, cargo, personnel, all the sustainment that we need. We need to be able to do that at points of our own choosing. We need to be able to do it very quickly. In the past, landing craft would be susceptible to tides, susceptible to the characteristics of different parts of the coastline. With what our modern military needs are landing craft that, again, provide a lot of the flexibility that traditional landing craft maybe necessarily did not.
In order to achieve these ambitions, engineers have built an all-new generation of advanced amphibious vehicle. This is the Ship-to-Shore Connector, also known as the SSC. The US Navy's latest and greatest hovercraft. It's designed to carry some of the military's heaviest cargo into locations that were previously impossible to reach.
Welcome to the Navy's next generation air cushion vehicle, Ship-to-Shore Connector.
The SSC is the most capable and cutting-edge hovercraft on the planet. Nothing can compete with the SSC.
The Ship-to-Shore Connector can access over 70% of the world's coastlines. You can't do that in any other vehicle.
Piloted by a crew of 4. This giant hovercraft measures in at nearly 15 meters wide and over 27 meters long, or the equivalent of 3.5 London buses, making it the US Navy's largest amphibious landing vehicle. It can carry some of the Marine Corps' heaviest equipment and unload it in some of the planet's most hostile coastal locations, making it a vital tool that helps the military overcome the challenges of landing operations. At a state-of-the-art manufacturing facility in New Orleans, Louisiana, Navy Captain Cedric McNeil is overseeing the final stages of production of these brand new vehicles, as they prepare to begin testing after decades of development.
To say that we're excited to see that the craft are delivering and starting to get underway and we're starting to see how they operate at sea, that's an understatement. This is a culmination of the efforts of many personnel over the years to get to this milestone of an accomplishment.
And at an experimental research base in Florida,
Clear all day. Roger that.
Senior Chief Josh Pearsall and his crew are preparing to get underway in one of the first completed SSCs to have been delivered to the Navy.
Today's mission is operational test of the thrust system over water. We're going to be operating at high weight and power.
Engineers have created a craft like no other on the oceans. But how do you design a vehicle that can move seamlessly between sea and land?
It's extremely challenging to produce and engineer a craft that's meant for that kind of mission. You have to blend both aircraft-related technology with boat-building-related technology.
And how can you build a craft capable of surviving the punishing demands of military operations?
We have to make sure our craft is designed to operate and execute in a myriad of environments,
whilst carrying tons of cargo at breakneck speeds.
The craft needs to be rigid enough to carry the heaviest of payloads and to be able to do so very fast.
The Ship-to-Shore Connector is the US Navy's latest and greatest amphibious vehicle. Built to conquer the planet's coastlines, it can hover above the sea and land to deliver troops and cargo into seemingly impossible-to-reach locations. Powered by 4 gas turbine engines that produce in excess of 24,000 horsepower. The ship-to-shore connector can reach speeds of 35 knots in waves up to 4 feet high, and transport a payload of either 145 combat marines or 74 tons of equipment, enough to carry the Abrams M1A1 tank fitted with full-width mine plow. At an advanced manufacturing facility in New Orleans, the first of these brand new craft are being constructed by a team of elite engineers. And as Navy Captain Cedric McNeil knows, once the finished vehicle enters active service, it must be able to access environments that would be impossible to reach with other landing craft.
The uniqueness of the platforms that the Navy and Marine Corps team are working with industry to design have to be able to be better than just a normal craft or a normal boat. So when we talk about a deployed scenario and the lack of infrastructure in a foreign location, we absolutely have to provide solutions that allow us to execute these missions across a myriad of scenarios. Our challenge, meet that mission of ship-to-shore transport of people and material.
To find an answer, engineers must look to the innovators of the past. Once upon a time, the only way to move troops and equipment ashore would be by boat. Ideally, into a harbour full of cranes. But when it comes to military operations, such luxuries aren't often available. The only option might be a beach, which is tricky enough in itself. And there could be all sorts of obstacles between you and it. On the British coast, physicist Andrew Steele has travelled to discover the secrets of an historic military innovation.
To you and me, this just looks like a cold day at the beach, but to engineers in the military, this represents a challenge. How can you move seamlessly between land and water and back again without having to spend ages loading and unloading boats? And if you're in the military, basically being a sitting duck.
It's a problem English engineer Sir Christopher Cockerell spent years attempting to solve. Eventually inventing a whole new type of vehicle, the hovercraft, eliminating the boundary between sea and land.
This amazing machine is the SRN-5, the Saunders Roe Nautical 5 hovercraft. And it's the world's first production hovercraft, based on the pioneering work of Christopher Cockerell. And isn't it beautiful? It looks sort of retro and yet futuristic at the same time.
After making its debut flight in 1964, the SRN-5 was the first hovercraft to enter military service.
This craft was a real trailblazer. It's still got essentially all the same technology as powers a modern hovercraft. And this was the first commercially successful hovercraft in the world.
The SRN-5 was the result of more than 5 years of research and development. Capable of floating across both land and water, Cockerell's game-changing technology would go on to transform the nature of amphibious operations.
Given that this vehicle can do something that sounds miraculous, hover in mid-air and move over almost any kind of terrain, it's really based on some surprisingly simple physics. One of the big innovations in the SRN-5 was that enormous Rolls-Royce engine at the top there, which is powering the whole hovercraft. And what does it power? Well, the first crucial thing is this fan in here. It doesn't look like a fan that you might normally see. Its blades are vertical. It's something called a centrifugal fan. And this fan acts as the lift fan. It's the crucial thing that makes this a hovercraft. It sucks air from the atmosphere and uses it to fill up this enormous skirt underneath the vehicle and lift it all up off the ground, reducing that friction.
To make the hover work, air from the fan is channeled into a thin curtain around the perimeter of the vehicle, lifting it off the ground and trapping a cushion of air under the hovercraft.
The second critical part of this vehicle is that there, the thrust fan, an enormous set of rotor blades. And what that does is sucks air and pushes it backwards, thrusting the hovercraft forward. Another critical innovation on the SRN5 is this thing, the hovercraft skirt. It traps the air, meaning less of it can escape. And because it's made of this flexible, rubbery material, it can adopt the contours of whatever terrain it's moving over, giving it incredible flexibility. And yet it makes the hovercraft so much more efficient. And that's why this is still used on hovercraft today.
Andrew is going to see for himself how Cockerell's brilliant concept works.
This beauty is basically a modern version of the SRN5, and it operates on exactly the same principles. So, let's get those fans going and fire this baby up. We're just driving straight towards the sea, which was completely crazy. That is bizarre. Just drove smoothly from the beach straight into the sea. It is a chilly morning out here.
By flying on its air cushion, the craft can transition between land and sea without stopping. A game-changing innovation that revolutionized landing operations.
Now the hovercraft's up and running, we've got that lift fan blowing the air into the cushion underneath us. We're just hovering out here. It's amazing to think that we're just being supported by a bed of air. Just 30 centimetres of air is what stands between us and the water now.
More than 60 years on from its introduction, the hovercraft has helped redefine how the military moved from ship to shore.
You can really see why the hovercraft was such a breakthrough. It's such a simple idea, but it's such a powerful, versatile vehicle. One of the most versatile on the planet. All right, Ben, take us home.
By supersizing the air cushion innovation pioneered by Cockerell, the SSC is capable of a feat no other hovercraft can match.
We can reach up to 70% of the world's coastline on the hovercraft. We can make a landing almost anywhere on the planet with this technology.
Today, pilot Josh Pearsall and his team in Florida are preparing to put the advanced air cushion to the test on one of this amazing new vehicle's first ever flights.
Hovercraft is disengaged. Alright, you're clear on deck. Roger that.
By flying 6 feet above the surface, the SSC can overcome issues that would make access impossible for traditional landing craft. Hovering over obstacles on the shoreline and continuing onto almost any terrain to deliver its cargo.
It allows us to go almost anywhere over water and land itself. Whether it's sand, dirt, ice, you name it, it can go there.
In Louisiana, engineer Ryan Schaffenocker has access to the impressive inner workings of the oversized air cushion.
So I'm standing inside the bag of the SSC. Directly above me is where we installed the lift fan volute. Inside that volute is the lift fan impeller. The impeller drives air through this duct inside the bag and also drives air upwards through the bow thruster.
And in order to enhance Cockerell's early design, the SSC's engineers are utilizing an updated take on his skirt system.
So here we're installing the advanced skirt for the SSC. It is a vulcanized rubber over Kevlar fiber reinforcement. The air cushion works via the lift fans. So through our main engines, we transform that power through the lift fans and drive air pressure into the skirt. The skirt is a bag and finger type system. The fingers direct that air pressure to the exterior of the craft, providing its lift.
By powering two giant fans, the enormous skirt is filled with air in a matter of seconds. Hundreds of individual fingers wrap around the perimeter to create a curtain of air that lifts the SSC off the ground. Each finger can move independently, allowing them to flex when traveling over uneven surfaces to improve ride quality and handling. And the small cross-section of each finger helps reduce friction to enable increased speeds.
The advanced skirt for the SSC allows for us to provide the maximum amount of speed and maneuverability possible. It's able to traveling at 35 knots. It's able to cut sharply for turns while maintaining the maximum amount of stability on the craft. The skirt is the key for the craft. It's what makes this an air cushion vehicle, right? It's what makes it fully amphibious. Without this technology, it wouldn't be able to perform the mission.
But the SSC requires more than just its advanced skirt to operate effectively.
A key factor in enabling us to be able to transport people and cargo to the beach is speed. We're in a contested environment oftentimes. We're against an adversary, and we need to be able to quickly maneuver so that we can support and execute our mission in a timely and efficient manner.
And the key to achieving this objective is plenty of power.
What we have before us here is the Rolls-Royce MT7 gas turbine engine. There are 4 of these on the SSC platform, which provide propulsion.
These impressive engines drive a pair of thrust propellers that measure in at almost 12 feet across and push the SSC forward at high speed.
So let's look at the performance overall for the craft. We're looking at a top speed somewhere between 30 to 40 knots. This engine was selected because of its lightweight and its pound-for-pound punch in the way of power.
At the experimental test base in Florida, Senior Chief Josh Pearsall is one of the few people to have experienced the speed of the SSC firsthand.
I am very impressed by what I've seen of it so far. The advantages of being able to move fast is it allows us to rapidly deploy forces around the world and build up the force that we need in any terrain.
And as part of today's test flight, Josh gets to put these potent engines through their paces.
All right, here we go. Start in 1 and 2 Bravo. Start in 1 and 2 Bravo.
In combination, the SSC's engines produce around 40,000 pounds of thrust, the equivalent of a Eurofighter jet.
We got rotation all around. Roger.
And with such mighty mechanical muscle at its disposal, this all-new amphibious powerhouse will be able to accomplish its mission at previously impossible speeds. In order to move some of the US military's heaviest equipment into some of the planet's hardest-to-reach locations, engineers have introduced an awe-inspiring amphibious vehicle. The Ship-to-Shore Connector. Designed to be deployed from transport ships known as sea bases, the SSC can fly at high speed across the open ocean and deliver a payload with a weight equivalent to 11 African elephants into almost any terrain. But the requirement to launch its operations from far offshore can create challenges that the Navy's engineers and the manufacturing team in Louisiana need to overcome.
We're typically looking at going from ships that are over the horizons anywhere between 10 to 20 miles, and then allowing cargo and Marines and personnel to get from the ship to the shore. Typically, this can be in a contested environment, so we have to be agile.
All hovercraft of this type need to be able to launch from motherships, transition across the water, and navigate all sorts of obstacles on the way to shore, potentially including hostile fire.
There's absolutely no room for compromise. Agility is a core feature of design for this platform.
To help address this issue, engineers have equipped the ship-to-shore connector with a trio of steering solutions.
The SSC platform is designed with 3 primary effectors for maneuverability. Those components are the controllable pitch propeller, the rudders, and the bow thruster. What you see before you are 6 controllable pitch propeller blades. The 2 rudders you see on the port and the starboard side provide maximum steering capability for the platform. 80% of the craft's maneuverability factors are controlled right here with the rudders and the controllable pitch propeller blades.
By adjusting the pitch of the propeller blades, the amount of thrust generated can be varied. When blade angle is increased, more thrust is produced. And when the blade angle is decreased, thrust is reduced. The rudders then interrupt the airflow coming from the propellers, pushing the stern of the craft in an opposing direction.
The bow thrusters provide that fine-tuning aspect of maneuverability. When you're operating in a docking environment or near structures, the left to right motion or the lateral movement of the craft is what's provided by the bow thrusters.
By directing a stream of pressurized air from the SSC's lift fan through a rotatable nozzle, bow thrusters move the craft in the opposing direction. Off the coast of Florida,
Just enough to get through the bridge.
Senior Chief Josh Pearsall is testing out the SSC's agility. Under his direction, the pitch propellers, rudders, and bow thrusters work in combination to precisely maneuver the craft.
All right, here we go. Roger.
Capable of seamless transitions between forward, reverse, and lateral movement, the SSC can even turn 360 degrees inside its own footprint, allowing it to navigate through congested terrain without issue. But agility alone is not nearly enough for the SSC to meet its mission. It needs to be strong enough to carry giant cargo, while still remaining light enough to hover over the surface.
A key consideration in the design process for SSC is weight and weight savings. We have to ensure that there's a balance between what each component weighs with how much payload we can take ashore. The bottom line for SSC is every pound matters, whether we're talking that from the perspective of weight savings or how much payload we can take ashore.
In order to find a solution, the SSC's engineers must look to the pioneers of the past. To help humans take to the sky, early planes were made of wood. But while this lightweight material was easy to get off the ground, it lacked the strength to carry anything more than a pilot and a passenger. To build bigger planes and carry cargo, engineers opted for steel. But this heavy metal had its own problems. It made it almost impossible to get airborne. Engineer Dan Dickrell has travelled to the Military Aviation Museum in Virginia Beach to discover an incredible piece of aeronautical history.
This is the Junkers 52. It was the first cargo plane made out of aluminum. Look at this thing. It's immense. Feels like modern aviation has arrived.
Designed by Ernst Zindel, the Junkers 52 made its maiden flight in 1930. And its revolutionary all-metal construction meant it could carry an impressive 3,000 kilogram payload. A huge advance from wooden airframes.
As you can see on the side, there's a large door meant for loading cargo. You can imagine troops loading fuel, ammunition, supplies inside. And if I climb up this ladder, you get a sense of how much space is in here, all of this volume. You can imagine all of the supplies that could fit in here and the soldiers getting ready to fly this plane into battle.
But a key factor in making the aircraft capable of carrying all that cargo is the skin.
On the side of the aircraft, we can see this unusual corrugated shape. That's because this aircraft is made almost entirely out of aluminum alloy called duralumin, which was discovered by Alfred Wilm.
Wilm was a German metallurgist, and his breakthrough alloy would go on to revolutionize aviation engineering.
If we look at this inspection panel, you get a good sense of how this aircraft is constructed. You can actually see the structural elements that compose the aircraft, and then also you can see the skin. This is all made of duralumin, that really, really strong material that enables the plane to carry as much cargo capacity as possible.
By manufacturing from a metal that was both light enough for flight and strong enough to hold heavy payloads, the Junkers proved that airborne cargo transport was possible.
This plane, as big as it is, it only weighs about 5,600 kilograms, or about 6.5 tons. It's a remarkable airplane.
Incredibly, Wilm's innovative alloy was invented entirely by chance.
What I have here is a regular piece of aluminum, nothing special about it. It's not very strong, it's quite bendable. This is not very well suited for use in aircraft. Wilm knew this, and so what he did is he tried to employ the same techniques that were used to strength harden steel. So how we do that is we create an intense source of heat. In this case, I'm going to use this blowtorch, and I'm going to heat treat this piece of aluminum. If we were going to do this on steel, the same technique would be to heat it up to around 700 degrees Celsius. And then you quickly quench it. And then we check and see, have the strength properties of this aluminum changed? It's still quite bendable. And this was very disappointing to Wilm. So he had left his laboratory, his tools, and he came back a few days later and re-examined the aluminum. And what he discovered was this. It looks the same, but this is age-hardened aluminum. When I try and bend it, it's a lot tougher. And this was the magic behind age-hardened aluminum, that over time, the atomic structure had changed, enhancing its mechanical properties. And that's what makes this material brilliant for aircraft usage, is because it is very light and it is very strong.
Wilm's accidental discovery went on to totally transform the aviation industry, with many modern aircraft still built with age-hardened aluminium.
Without the invention of this amazing material, the idea of cargo-carrying flight would still be impossible.
At the experimental test base in Florida, Marines Colonel Paul Merida knows that the ability to move more cargo can be key to the success of an operation.
A lighter landing craft is an increased payload. That means more troops, more vehicles, more combat power, and more sustainment ashore. The reason that's important is because the quicker that we can get our combat power ashore, the faster we can prosecute operations once we hit the beach.
By adopting Wilm's aluminium innovation, the SSC is both strong and light enough to transport a payload almost 22 times greater than the Junkers. A staggering 74 tons.
The SSC allows us to carry extremely heavy loads, like some of our heavier trucks, some of our artillery systems, and some of our armored vehicles.
At fully loaded capacity, this exceptional hovercraft can move the equivalent weight of 30 Humvees, an essential ability that empowers the troops on the front line.
These vehicles are important to our operations because it gives us mobility, gives us speed, and inherent in that is extra firepower as well.
At the factory in New Orleans, the engineering team are working with this amazing metal as they ready another vehicle to roll off the production line.
So to construct the hull and the above-deck modules, we use 5083 aluminum.
It's a choice that's undoubtedly influenced by Junker's pioneering cargo plane.
Aircraft and the SSE share a similar design. They're both very, very sensitive to weight. So the way that aircraft are constructed using aluminum, just very similar to this, the same kind of structural engineering approach, the same type of materials.
But the demands placed on the SSC means strength is just as important as weight.
The SSE is designed so that you can carry very, very heavy payloads, including the Abrams M1A1 tank. That tank needs to be able to roll on top of the SSC. So the modules that we designed for the SSC need to be able to withstand those kinds of loads. In this cell, we're building up the fixed and deployable ramps for the SSC. You can see the stiffeners that are used to strengthen up the module. We use 5083 aluminum plate and extrusion to build these and then install them on the craft. Selection of this material is critical to the success of this vehicle.
The ship-to-shore connector is the most advanced hovercraft on the ocean. Built to deliver US troops and heavy cargo into hard-to-reach locations, it's the ultimate amphibious vehicle. Driven by a pair of propellers that measure almost 12 feet across, the SSC can hover on a 6-foot cushion of air and fly across the water and onto 70% of the planet's coastlines to deliver its outsized payloads, an achievement unmatched by any other landing craft.
Beach and surf appear to be clear, port and starboard side.
In Florida,
Making our approach back onto the ramp.
Senior Chief Josh Pearson and his crew are returning the SSC to base after a successful test drive.
And go ahead and bring us off cushion.
But if this brand new vehicle is to achieve its objectives once it's deployed for real, it has to be tough enough to survive the rigors of military operation.
Shut down all main.
When you look at the different environments that we're called upon to operate in, it's some of the harshest environments on the globe. And SSC has to deliver, has to be able to take Marines and their cargo from the ship to the shore.
And in order to survive in the near impossible conditions of corrosive saltwater, abrasive sand, and punishing extremes of temperature, the SSC must be built to last.
We have to consider is our ability to maintain the craft as it operates over its 30-year service life. We're talking about wear and tear on the vehicle, individual components, how long they last, how durable they are. Each component has to have that factor of consideration before we install it or incorporate it into the design of SSC.
In order to accomplish all this, engineers must look to history's great innovators for inspiration. In Evansville, Indiana.
Hi, Rick.
Hello, you gotta put this on. Okay.
Professor Mark Valenzuela is about to take a once-in-a-lifetime ride on an icon of military engineering.
So I've got to be careful.
This is an LCVP, or a landing craft vehicle personnel, one of the most important vessels of World War II.
We're being lowered with this davit contraption here. We're doing a little bit of rocking, but I have every confidence in this crew. And now we're safely in the water, I believe. Okay, good. Just thinking about 36 men kind of anticipating their arrival onto Omaha Beach in a boat like this is kind of amazing.
Built to navigate the challenges of shallow waters and land troops directly on the shores of Europe, the LCVP was a game-changing innovation. But its design was far from perfect.
The original ones were made out of wood and wood panels. So that would need to be pieced together using screws and bolts. Anytime you create that hole in the material, you're really compromising the integrity of the material.
To improve the durability of the LCVP, military engineers needed a new material. Thankfully, an inventor by the name of Games Slater had made a discovery that could help solve the problem. By bonding glass fibers inside a hardening resin, Slater invented a reinforced plastic known as fiberglass. Stronger and lighter than steel, and highly resistant to rot and extreme temperature. It was an ideal solution for building a new and improved generation of this iconic landing craft.
Here it is, the fiberglass LCVP, and it is a magnificent boat.
First deployed during the Korean War, the redesigned LCVP is the earliest known military vessel to be mass-produced from fiber-reinforced plastic.
We can kind of get that sense of that fiberglass, that hollow thumping sound. This is in beautiful shape.
And the introduction of this incredible composite material offered the new LCVP a number of advantages.
In terms of that manufacturing with fiberglass, we can make it as big as we want to. So we aren't limited by the size of the planks that we would use in regular plywood. And so because we can fabricate it in fewer pieces and fewer joints, there's going to be fewer weaknesses associated with all of those joints.
By building from fiber-reinforced plastic rather than wood, the durability of the LCVP was totally transformed.
So we can kind of imagine plywood panels that would be used to form the shape of this hull. And as these two pieces of paper just kind of butted against each other, we need some way to be able to hold these panels together. What we could do is kind of simulate these mechanical fasteners just using these staples. But once I start to introduce these staples, those holes then become these points of weakness in this material. It might actually be easy for us to be able to break them open like this, especially along those joints. And so you'll notice that the failure is actually all along that. So this is one of the weaknesses that we see with the use of plywood. The advantage, of course, with fiberglass is to be able to use one continuous sheet that doesn't have to rely on any of these joints or any of these mechanical fasteners. And try as I might, I'm going to try and pull on this paper and try to break it. And of course, we're not going to see any sort of breakage because there aren't any seams and points of weakness there.
Thanks to the introduction of reinforced plastic, many fiberglass LCVPs are still seaworthy, while none of its plywood predecessors are.
Taking a look at this marvel of engineering from the 1950s, and I'm just kind of in awe of my engineering ancestors.
Today, at the production facility in New Orleans, Ryan and the team are relying on fiber-reinforced plastics for key components of the SSC.
So we're using composite technology, the latest epoxy in carbon fiber. We use that for our lift fan volute, the bow thruster, our drive shafts, the prop duct, the rudders, as well as the propellers themselves. Composites are very corrosion resistant by their nature, so they're able to withstand the very difficult operating environment, for instance, salt water and those kind of heavy humidity environments.
And just like the pioneering landing craft of the past, the SSC's maintainability is improved through its use of these innovative materials.
Using composites allows us to reduce the total part count on this craft and also allows us to achieve some very complex aero shapes, such as the lift fan volute that you see behind me. And we're allowed to do that with fewer parts. We were able to achieve these shapes by molding the parts all in one. So with having fewer parts, that's less parts that you have to maintain, so that improves the lifetime of the craft.
Thanks to the impressive engineering behind this amazing machine, the challenges of moving from ship to shore can be easily conquered.
The SSC is absolutely one of the most amazing vehicles on the ocean, or the land for that matter. This vehicle can do things that no other vehicle can do.
The capability of the SSC is amazing. It's definitely in a league of its own. It's next generation, and it's going to allow the Marine Corps to get combat power ashore much, much more quickly than currently.
By looking to the pioneers of the past for inspiration, adapting their ideas, updating their designs, and overcoming huge challenges. The SSC's team have built a boundary-pushing piece of amphibious engineering and succeeded in making the impossible possible.
The ship-to-shore connector platform is absolutely one of the most amazing platforms you'll ever see at sea. It's simply in a class of its own.